How to close this? I want to close this. It is, I don't find close. Oh, that one. Oh, no, let's close it then. I'm not. I didn't get that one. The one what? Let's get that. My pillar is still there. Yeah, correct. Okay. This is enough. I can find it. Oh, this only copy in the same the panel over there. Same place. I don't know what is there, no? Only two arranging this and that earlier one. Here I can put the. That's it. No, no, nothing. Only these two. But now I open that, then my presentation time. That, what is that one? Only one. That's all. I want to go to Rasul for one. No. Yeah.
Hello, hello. Audio check. Audio check. 1, 2, 1, 2. Hello, hello. Check. Hello.
What's wrong?
Good evening, everyone. So, are you all enjoying the session? Like learning something new? Yeah, just I know it's evening, but yeah, let's have some more fire. So, to start the session, I'd like to call our professor, Dr. Somojit Roy, to say a few words about our next speaker. Guys, let's have a round of applause.
So very good afternoon. So now our next speaker is Professor Shamar Kumar Dash. He's a very well-known scientist with a lot of accolades. So he has more than 200 research papers in leading journals, and he's a fellow of all the academies here in India. And he will be talking about supramolecular aspects of oxometalates in the light of crystallography. So you have been doing the classes on crystallography. You have seen the soft matter aspect of crystallography. Now you will see aspects of application in oxometalates in crystallography. So please join me in welcoming Professor Shamar Dash. Thank you.
Good afternoon, everybody, and thank you, Somojit, for inviting me and for giving me this opportunity to speak about this very important aspect. Before I start, I, I must tell you that although I wrote in the light of crystallography, I am not crystallographer by training. I do inorganic chemistry and mostly the polyoxometalate compounds. But with crystallography, we know what is there, what kind of supramolecular interactions are there, how it is helpful to understand the system. Once you know by crystallography what is the system we got, then we can explore a lot of interesting chemistry application in the inorganic chemistry or materials chemistry. So uh, already you know the what title I mean. So because I tell about crystallography and oxometalate means polyoxometalate. So let me begin with, because many of you know that inorganic chemistry textbook, when we say one chapter is there, isopolyanion, heteropolyanion, they are nowadays people coined as polyoxometalate. Okay, so this is I'm talking about polyoxometalate, many oxo, and because mostly they are anionic in nature, that's why metalate, like sulfate, carbonate, that's why metalate. Now, the best example I have given here, that is this polyoxometalate known as phosphomolybdate. Okay, this long back it was synthesized. Okay, crystallographically was characterized also many years back by the scientist called Kegin, Keggin, Kegin. So that's why on his name is called Kegin anion. Okay, now you may wonder the why choose this one, because when you do the BSc practical, the phosphate test, phosphate test, what we do if you want to know is a phosphate or not, we take some molybdenum source, ammonium molybdate, heptamolybdate, sodium molybdate. If phosphate is there, we acidify to end up with very nice, canary yellow color, precipitate immediately. So the why it is formed, because this cluster is formed. This is the reaction, overall reaction to get this. If we use really ammonium heptamolybdate and sodium hydrogen, disodium hydrogen phosphate, we acidify. You not necessarily have to put nitric acid. You can put also mineral acid, hydrochloric acid. You end up with this compound, and this is the crystal structure. This is the polyhedral representation. I'm not going detail, but definitely the 12 octahedral MO6 units are there, then 8 share and corner share, and overall you get -3 charge. If you take into consider +6 here, and phosphorus +3, then you get the overall this, sorry, phosphorus +5, then you get this cluster. And ammonium salt you can isolate that. Why I am talking about? Because crystallography help us to understand the structure, and then lot of applications we can see that. Okay, so one thing you must know, polyoxometalate if you want to synthesize, or this is a heteropolyanion. When you have other than this, only molybdenum, you have another metal, another element like phosphorus, sometimes silicon, sometimes boron, that is called heteropolyanion. If it is not there, only molybdenum and oxygen, is called isopolyanion. Okay, so I'm dealing with here one heteropolyanion. What is the basis of formation of this oxometalate? Basis is, when you, let's say start with even heptamolybdate in water, it comes into first molybdate form, tetrahedral molybdate with the 4 oxygen double bond. Then it will be, you acidify, the lone pair of oxygen takes proton, it will form. Then finally the coordination gets expanded from tetrahedral to octahedral. Then there's some condensation happens. So from OH, what will come out? MO form. That is the basic how this cluster form. Okay, even if this same thing happened in zeolite formation also. If you remember zeolite Y, aluminum silicate, same thing, AlOSi, SiO, Si, AlO, Al. So same basic reaction happens, and you get the product here. So one thing is sure, there's a limitation here. Polyoxometalate, if you want to synthesize fine, you can get lot of application, you can get crystal structure. But remember, when you do chemistry in water, because they are formed in acidic medium, you cannot deal this complex in alkaline medium, because reaction will go other way, it will be hydrolyzed and compound decomposed, isn't it? So because it is formed acidified medium, you can go up to pH 6, at the most 7, some compounds stable in the neutral pH also, but definitely you cannot handle them in the alkaline medium, it will be decomposing. Now I'll give you some representative example. What are the polyoxometalate known? Many, plenty of. I have chosen very versatile one. One is called link. This is called MO6O19. I told you isopoly and heteropoly. It is isopoly. There's no other element like phosphorus here. It is not there. One is decaphenatate. Very versatile. Very well known. If you take decaphenatate, sodium phenadate, water and acidify, you get nice orange crystal within few hours. Decaphenatate. You have paratungstate, again isopolyanion. You have Kegin, just now I told you, phosphorus Kegin is the cobalt centered Kegin. Cobalt instead of phosphorus, cobalt centered, tetrahedral cobalt, and WFO40. I like to draw your attention about this compound much because I will tell you more story about this compound. Okay. And very interestingly, recently we saw this compound, if you can encapsulate in a confined space, it get hydrolyzed to COW12O44. Remember, it is COW12O40, 3 minus. If it get hydrolyzed, it will form COW12O44, 14 minus. Okay, that we recently we saw by crystallography. And other than this range of clusters, you can get also very big cluster, medium size MO36 cluster. You have also very big cluster MO154, giant clusters, discovered in Posaki Muller lab, where I, Somojit Roy, we work same lab. Okay, so we have some experience how to synthesize this big giant cluster also. So these are the representative example of polyoxymetallic clusters. And I like to draw your attention about this compound particularly because this compound, we have done recent time lot of research, lot of interesting applications also. Now, what we do with this polyoxymetallic compound? We do a lot of water splitting, mainly electrocatalytic. Recently we started photocatalytic also, but today I'll talk about mainly electrocatalytic water splitting. Okay, you know that in the electrochemical cell, the anode you get oxygen, in the cathode you get hydrogen, and if you see the fundamental reaction of this half equation, they're not very easy. You need a very good catalyst to get it happen, and in nature it happens. Water splitting in the photosystem too. In the photosynthesis, one manganese oxocluster is there, tetranuclear oxocluster. That is the catalyst to do that. So I'm talking about we need some catalyst to do that. Now, today I tell you mainly polyoxymetallic centric some systems, mainly supramolecular chemistry. And supramolecular means if you want to know, you have to know what is structure actually by crystallography. So the compound I am showing you mostly we characterize by single crystal X-ray crystallography. Mostly some of them we could not. In that case, we have to take help of the PXRD matching and all these things. So I'll talk about complete encapsulation because you have a framework material. You can completely encapsulate your active species and you can do some interesting applications. You can attach a cluster surface some active species. Let's say I know one tensile metal aqua complex is very active. You cannot handle just like that because it will dimerize all this thing. But if you coordinate covalently attached to the cluster, it will be heterogeneous, insoluble. You can do catalysis. And also I've showed you interestingly, an intercalation chemistry, intercalate between the MO3 layer, the graphite like MO3 layer. You can intercalate some of the active species. You can see interesting chemistry. Again, intercalation we knew by crystallography. And of course, sometimes we also do just coulombic interaction, supramolecular interaction. They are not encapsulated, they are not intercalated, just they are side by side, but by hydrogen bonding interaction they are remaining and they give fantastic properties which otherwise not possible. So today I'll talk one very interesting story about this polyoxymetalate and this metal aqua complex. These together, the supramolecular interaction, how they make very interesting chemistry. Now let me begin with one very interesting complete encapsulation host gas system. What I mean is that I told you some time back one cobalt Kagan, the cobalt center Kagan. This is the structure. In the center, cobalt tetrahedral W12O46 minus. This cluster is known long time back. Just okay. In fact, this Z8, what I am telling you, it is also known. It is nothing unknown. It is originally one Chinese group synthesized, then it became popular. Omoriagi group, popularized, and they gave the name Z8. Okay. Now, what we found when we take electrochemistry of this particular Kagan, known Kagan, it gives cobalt 2,3 couple. The blue one. Cobalt 2 goes to cobalt 3. This fundamental chemistry, I must tell you, cobalt 2, we cannot make here cobalt 4. not happened. We have checked by detailed electrochemistry, only give cobalt-3 to couple. Okay, very interestingly. If you want to temper it, let's say very high, alkaline pH, it decompose. I already told you, any polysometalate alkaline pH decompose. If you put very high potential, it can go to +4, but it will be decomposed. It will not remain Kagan factor. Kagan is very particular. Tetrahedral, 4-oxo, then you get 12 WO6 connected by 8 sharing, corner sharing. So that if you want to temper it by doing forcefully, it will decompose. But it's very otherwise very stable structure. Because it's give 2-3 couple, we wanted to check when you put inside the confined space, what happens? These are main idea. Interesting thing is this cavity, this internal cavity diameter, it is 11.4 angstrom. And if you check from here to here, it is around 10.8 angstrom. That means size matches. Not that first time we did. It was known by a British group that not this Kagan, silicon Kagan was put in this mold. Why we took the cobalt is the redox active. This is the idea. So we took that and we encapsulated. How do you encapsulate? It cannot do just like that because there's no just window or pore it will go inside. Okay, although size fits, but it cannot go inside. You have to do in situ. That means zinc and 2-imidazole ligand, if you just mix in alcohol, this framework form very easily. So what we did, we pre-synthesize, we first synthesize this compound, potassium salt, okay, water soluble. Then it's also soluble in the partly in alcohol, methanol. Then in situ synthesis we apply. In situ means we took zinc 2+, zinc salt, and we took the 2-imidazole ligand, and we kept this compound here. So when the MOF form, metalloorganic framework form, some of them it will be get encapsulated. Now let me tell you, we don't have the control of the encapsulation. Control means what? We cannot say that I want all cages to be filled. No. Whatever way we did, we always find that one cluster goes in 7 cages. So this happened like that. The compound, this is a compound form. We have kept less amount, more amount, but if we put very less amount, we cannot get all filled. But generally, we get one cluster per 7 cages. That we characterize. We don't get single crystal for that. For this one, we got always microcrystalline compound, PXRD, all these things, and characteristic property of this. We proved that this compound got encapsulated one cluster per 7 cages. Okay. Now let me tell you interesting things. As such, Kagan gives 2-3 couple. Okay, over 2 to 3. No oxygen evaluation. Once we put inside, the feature completely change. You see, whenever you get the huge current surge, that means oxygen bubble come, and you can say the oxygen is forming. Not only that, this compound see continuous oxygen bubbling like 24 hours on these things, and it works in the neutral pH. Now I told you the Kagan compound, polyoxide compound, they are generally decompose. In alkaline medium, definitely it will decompose. Neutral medium, it may decompose, but because we encapsulated, nothing happened. 24 hours, we give oxygen. Again, we keep the same, electrode use after 7 days. We will continue the same thing. Because it is a heterogeneous system. No, what we do, we coat on the electrode. And let me tell you, heterogeneous how we do. The material water insoluble, we coat on the working electrode with some carbon material, and naphthalene we use for binder, and it will be coated nicely, then it will not come out. Then we do the electrochemistry. And what we do, we find out 3 parameters: periodic efficiency, and turnover frequency, and over potential. Over potential should be very low, like within 300-400 millivolts. There is a good catalyst. Periodic efficiency should be 90%. Then no other reaction going on. And of course, we check the stability, how stable it is. So, very surprising thing, as such, the compound giving 2-3 couple, 3 to cobalt 3 to couple, but this compound, when we put inside, suddenly what happens? It is giving oxygen bubbling. Question come to us because we are inorganic chemists. Then maybe something happened, the cluster got decomposed, but inside in the cavity, if we decompose also, it will be remaining like that because we characterize everything, we are getting electron spectrum, all these things. Then what recent time what happens is we found, it is this very recent time, when we published this paper, we wrote that only, that as if this, cobalt W12O40 inside the case earlier. Recent time we put this, same cluster another MOP, okay, copper MOP 199. It is BTC, benzene trichlorophenol, very well known MOP. So in this case, we got crystal structure, single crystal. We could, of course, very high symmetry in this thing, and then we found we could locate this, cluster inside. Earlier study we could not get single crystal, only PXRD. Here we could locate, and then we found that MO, it was tetrahedrally bound, no, earlier, that cobalt 4, but here we found 8. Cobalt is connected to 8 oxygen, as if it is inside a cube. Then naturally, question comes, we also find like that. I mean, let's say these oxygens, tetrahedral oxygens are Gibbs over 2 position. If one oxygen is half occupancy, Gibbs over 2 position, it look like will be octahedral only. Okay, but in this case, we checked 2-3 times again. We measured the crystal. We got full occupancy of each oxygen. We really actually happened that cubahedral. I mean, a cube, then cobalt is in the center. That means it got, if chemistry has to happen, it got hydrolyzed. Hydrolysis is what? Cobalt W4O46 minus water, and it will form cobalt W12O44, 14 minus and 8. Okay. Then still we are not comfortable, because when I submit the paper, definitely somebody will ask question. We are dealing with G solar, all these things, who knows. Then recently we found 2-3 papers appeared, and they got same thing what we got. So that means earlier paper what we published, what we thought it is cobalt W12, O40, we strongly believe it was cobalt W12O44, because now we checked carefully Raman and all this study. The Raman spectra, little difference between this and this, but the Raman spectrum we are getting now of the encapsulated one look like very much this, where I could not get crystal structure earlier one. So we believe that this is the compound form, and that give both couple cobalt 223, 324. Okay, now it makes sense why upon encapsulation it gives oxygen evaluation by electrochemistry, because we believe that cobalt cluster hydrolyzed to this cluster, and now this gives 2 couple cobalt 2,3 and cobalt 4,3 and cobalt 3,2. Now you may ask me, how do you know this compound will give this 2 couple? Because now it is published by others. We synthesize this compound and do the CV of that compound, and that gives exactly the got CV here, no, like that. That means definitely in our earlier paper what we published before, although we thought it is nothing but that cobalt 2, that cluster, the cobalt 2 WLO40 is not O, it is O44. Okay, so that gives the continuous oxygen. So that means very interesting encapsulation happened. And here is the very powerful tool, crystallography. Unless we did not know this thing, we would not know the earlier case of this happening. Okay, so this way story begins, and you can see how encapsulation makes difference. A compound which is electrochemically inactive, I mean, towards water oxidation, it gives water oxidation, but by getting hydrolyzed. And we found out all these parameters: turnover frequency, 10.8 mole of oxygen per second is not bad. Fatigue is also very good, close to 100%. So it is a good catalyst and work in neutral pH. Now, because I am talking about polyoxometalate, you saw there that a central cobalt became active because it hydrolyzed, and it gives 4,3 and 3,2 couple. Now I am telling about another interesting polyoxometalate. We could get single crystal. You see, let me tell you what is this again. Same again, SiW12O40. But if you take out one WO, okay, then it will be SiWLO39. So taking out, no, you put the another metal, bismuth and water, these 2 water. So bismuth you can put if you can make it lacunary. What is lacunaric again? If you take out one WO from Si W12O40, it will be Si W11O39, and that lacunary place you add one another metal, heteroatom bismuth, and you get this compound. Now we are lucky enough, we got the single crystal structure of this. Remember, now we are talking about bismuth in the periphery, not in the central. Central is actually silicon, but bismuth in the periphery. So by single crystal structure we found out, and this compound we wanted to do some chemistry. Why? Because although silicon again as such is not very active towards any water splitting or anything, because bismuth is there, bismuth 3 can go to bismuth 4, can go to bismuth 5, and you can get water oxidation. So that's why we started. But problem is this compound highly water soluble, first of all, and again this particular compound, when you put in water, neutral pH slowly decompose. Because polyoxymetalate already told you, alkaline pH decompose immediately, instantaneously. Neutral pH also sometimes slowly goes. But this compound, this is a problem. That's what we thought. Earlier we thought we can encapsulate this compound in that same mop. So what we did, we take the same mop, Z paint, because these are size fit nicely. And why we did that? Because this bismuth, as inorganic chemist, we know bismuth 3, if you start, it can go until bismuth 5 oxo by 2 electron oxidation, and that will be very active towards water oxidation. It will oxidize water, come back to bismuth 3 and oxidate. So having that idea, we encapsulated there. Why encapsulate I told you? Because it is highly water soluble and decompose with 2 minutes. So once we put inside the this same zip, it is very stable. It doesn't decompose. It is first of all, it is heterogeneous now. It is not soluble because it is inside. If you remember, earlier we told you the cluster was 1 cluster per 7 kg. Here we got 2 cluster per 7 kg. Again, we have no control. Even if we put extra, it always take, in this particular case, 2 cluster per 7 kg. So we have kept one functionalized bismuth, POM, polyoxymetalate. How we functionalize? With bismuth aqua compound. Why we did that? Whole moiety is inactive, but bismuth is very active, and we can get water oxidation. Not only that, a miracle happens. The compound which is decomposed neutral pH slowly within 15 minutes or so, it is stable here forever. Ever means at least weeks and weeks and month and month. Nothing happens once you put inside. Then we wanted to check really electrochemistry, water oxidation. Now you see, very interesting thing happens. We can use very wide pH range from pH 4 to 7 to pH 13. pH 13, one polyoxymetalate, you cannot imagine it will decompose. It will be happening, just come back of monomeric oxo and molybdenate or tungsten. But here you can do even 100 cycle pH 13. You can do the neutral pH 500 cycle. You can do even 1000 cycle in the pH 4. pH 4 makes sense. Polyoxymetalate very, very stable. So he also get decomposed after 100 cycles. Slowly it hydrolyzed. Something happened because bismuth is here, slowly attacked. But you can see in the same platform in 100 cycle you can do fantastic chemistry, water oxidation in the wide pH range. So this is an interesting material in the sense the polyoxymetalate compound instantaneously decompose in alkaline pH. Here you can get stable catalysis for every 100 cycle. Now, so that was the approach. I'm showing only very briefly few examples. We have many examples like that. Now I'll show you the attachment, coordinate covalent attachment. Let's say you have a cluster, same Kagan cluster, and you have a aqua compound. Let's say nickel, bipyridyl, and water. Water ligand is very important because water ligand, when there, then only when you oxidize, it will form hydroxo and double bond O to make active species. That's why one water ligand is very important. So what we did last many years since I joined University of Hyderabad, we are doing lot of polyoxymetalate clusters, crystallography, supramolecular chemistry, but we never checked water oxidation. We did not know that. So recently we were trying to check, and what we found that this compound you can make potassium salt, water soluble. You can get ready-made nickel bipyridyl 2 chloride salt, water soluble. We attach coordinate covalent bond as if the cluster acting as the ligand, isn't it? Oxygen lone pair coordinate to the, by lone pair to the metal ion and make a very stable heterogeneous system, water insoluble. Now this compound, if you coat on the electrode surface, and we do water oxidation, let us see. Again, fundamental inorganic chemistry, nickel bipyridyl. I told you water ligand is very important. That will oxidize to water. Then Lewis acidity increase, so it will be one photon will come out. Then hydroxo, one more electron oxidize, nickel 4 will form. Again, more Lewis acidity, and it will be one more photon come, and you get nickel 4 oxo, and that will be very active towards oxidation. It will give continuous cyclic manner. It will give bubbling of oxygen. And again, we got very interesting parameters like what we wanted to have, that Faradic efficiency close to 90%, very good turnover frequency, and decent, and I know say very good over potential, decent over potential. You can make it cycle. We also did the CP and cyclic stability to 1000 cycle. It almost same, little bit different because of vigorous oxygen gas come out. Some code may come out. Just a kind little bit decrease. So you can do like that. Very interestingly, nickel compound give water oxidation. Now, when we do copper, similar bipyridyl copper, the same Kagan compound, we get hydrogen evaluation. Why? This is the beauty of metal ion, between the cobalt and copper. Copper case, definitely when we get water oxidation, metal has to go to hydrogen state, isn't it? Nickel goes to nickel 3, nickel 4, coming back, you are getting. Copper will get hydrogen evaluation. We don't get oxygen. Gas comes. When we put in the GC, we see hydrogen happening, of course, happening in the cathodic window. We believe that we should respect that soft and hard acid-base principle because copper is soft in nature and couple of nitrogen ligand is there. So it will like to be reduced rather than be oxidized because soft nature. So cobalt 2 will go to cobalt 1, and cobalt 1 will be very good reductant. It will reduce photon and give the hydrogen. This is the idea. Now one may argue with me that maybe I'm getting elemental cobalt, maybe compound get decomposed, the cobalt 2 becoming cobalt 0, and cobalt 0 is a good catalyst for hydrogen evaluation. Everybody knows that. But then we did a lot of control experiment. After electrolysis, we checked that material and we found no elemental copper. It is cobalt, always we find copper 2 only. So copper 1 form very unstable manner, very active, and immediately reduce the hydrogen to H plus 2 photon. That's why any resting time you say if you do this XPS everything you get copper 2. So similar system, when you put them in a coordinate covalent bond, you get continuous hydrogen evaluation, very stable catalyst, you can get that. So intrinsic nature of the metal makes this difference. We did a lot of control experiment, of course, because you may say that if copper bipyridyl aqua compound attaching the remaining same or not, but it may detach during the catalysis. So we did a lot of control experiment and we proved that only during attachment time it is stable and give continuous hydrogen evaluation. Otherwise physical mixture doesn't give. What I mean by physical mixture, you may take copper acetate, you may take copper chloride and bipyridyl mix together in a grind together and do the catalysis, it will not give. So this is the story of the heterogeneous system by attachment, coordinate covalent bond attachment. Now again I have to thanks to crystallography because by crystal structure we discovered something very interesting. What is that? This story of intercalation story MOO3. Okay, let me tell you because we do our MSc class practical and there's a one test called molybdenum. Sometimes we do test for tungsten. For molybdenum test, what we do, let's say sodium molybdenate you take in water, highly water soluble, drop wise you add hydrochloric acid, you get after some time some precipitation settled in the bottom. That is nothing but the molybdic acid, isn't it? This molybdic acid very well known. If we heat it, you get MOO3, molybdenum oxide. Molybdenum oxide again alpha MO3, epsilon MO3, metaphase, and one hexagonal MO3, another state. But thermodynamic stable state is the alpha MO3. Okay. Alpha is a very versatile compound. If you write in a search engine like SciFinder, alpha, just MO3, I'm not saying alpha, any MO3, you get close to 50% hit. That means 50%, 50,000 papers published on MO3. Very, very versatile. That means MO3, people use a lot of sensing application, catalysis, all these things. So you also wanted to do something. Again, this particular story happened serendipitous. We got crystal structure, then we came to know the story. So what we let me tell you also in this context something called molybdenum bronze. Molybdenum bronze you get in a textbook level inorganic chemistry book. It was discovered in Germany more than 100 years ago, 1896. What is molybdenum bronze? This MO3, it is a water insoluble neutral molecule, no? Molybdenum plus 6 oxygen state, and every oxygen 2 minus 2 minus 2 minus minus 6. So a neutral molecule. The framework extended structure, graphite-like structure, neutral. If you put in water, you get suspension. That means every MO3 compound is water insoluble. Now, if you reduce the suspension with sodium borohydride or sodium dithionite, let's take the suspension and add sodium borohydride or sodium dithionite, reducing agent. Immediately you get some, very nice red-brown lustrous color. That means something happened. What happened? That it was neutral molecule. Now it is reduced. Molybdenum 6 goes to molybdenum 5. So molybdenum 6 is D0 system, molybdenum 5 D1 system, EPR active system. So it is a mixed valent layer now. So that is minus charge now. To counterbalance the minus charge, negative charge, you need some cation. So sodium aqua compound get intercalated here. This is called molybdenum bronze. If you use potassium dithionite, you get potassium aqua compound. Lithium dithionite, you get lithium. So all are called molybdenum bronze. That means what is molybdenum bronze? Reduced MO3 intercalating alkali metal aqua compound called molybdenum bronze. Why bronze? They're shiny, lustrous, and they are electrically conductive. That's why it is molybdenum bronze. Although it was discovered in more than 100 years ago, 1896, alkali metal aqua compound is known, but one transition metal compound like copper or cobalt or nickel was not known. There we could contribute. We were lucky enough. Why it was not known, we did not know. We could get that again by single crystal crystallography. We just for MSc lab practical, same thing we use. Sodium molybdenate HCl, we use acetic acid and we use nickel. Although I write like that, it's actually nickel chloride 6H2. Formula, if you write in the bottle you see in any lab, the nickel chloride dot 6H2O. Actually, if you put in water, that form nickel hexaqua chloride. It's a coefficient complex. So, just mix them together. Within 6 hours, you can get nice, brown color crystals. And that crystal, when we solve the structure, we found out that MO3 in between nickel aqua complex, and it is not molybdenum bronze, by the way, because they are not reduced. I didn't put any reducing agent because it is plus charge. Something has to be there to counterbalance charge. So acetate get coordinate. Okay. In the asymmetric unit, it is like that. The MO2O6, one acetate, and 0.5 time, half of the nickel aqua compound and half of the water. So, sorry, one water. That means to make our life easy to understand what we do, when we write the reaction, we make it double. We wrote MO4, O12, 2 acetate, now one nickel full compound, because that's why we made it double. So this is the compound. So we have single crystal structure, this is the compound, and to a surprise, all MO3 compounds water insoluble. This compound is water soluble. This is very surprising thing, but all MO3 compound water insoluble is soluble. What is the logical explanation? We believe, we don't know the answer because we didn't do any computation so far, that because some electrolyte is there, because nickel aqua compound and acetate kind of electrolyte, that may be make possible to solubilize the whole system. It is a MO3 compound, not molybdenum bronze so far, intercalating nickel aqua compound, and it is water soluble. Not only that, if you dissolve the compound in water, pH becomes 3.8. Water pH 7, no? pH becomes 3.8. That means the compound is inorganic acid, isn't it? Why it is happening? Definitely, when you dissolve, some proton comes out. If proton has to come out, what is the possible thing? Definitely some deprotonation of the water. With inorganic chemists, we did acid-base titration, and we found out that one of the water actually get deprotonated and it formed like that. So in the solution, the compound you get nickel pentaaqua 1 O. Okay, so this compound formed, and that's why it is acidic in nature. Then we wanted to do electrochemistry because we know that nickel aqua compound electrochemically active. So this is the some structural parameters. It is a triclinic system. This is the, I told you, the asymmetric unit is the dimeric unit, and this I make some structure to show you the fully hydrogen bonding. Please, I like to draw your attention on this hydrogen bonding structure. See, aqua compound and oxo of the cluster and water highly hydrogen bonded, and that hydrogen bonding makes some difference that I am telling you the story. What is the story? I told you nickel aqua compound you can get easily from your bottle, from your lab, because it is nothing but the nickel chloride, NiCl2.6H2O, this compound only. This compound, if you take CV, you get this feature, one red feature, and after some time you get deposition. It is water soluble. But if you do electrochemistry for several cycles, you get deposition on the electrode and this give water oxidation. After some time, oxygen stops because those particles get agglomerate, then no catalysis. But nickel chloride, if you oxidize water, homogeneous solution, you get electrodeposition of nickel oxide, is nothing but nickel oxide, this red feature, and it gives water oxidation. That means nickel goes to nickel 3+ state, 4 state, then give water oxidation. Once it is there in the encapsulated and intercalated in the MO3, what compound you got, luckily this is also water soluble. I told you pH goes down. That when you do CV, what we found? Completely, miracle. This same person, the same species giving water oxidation, here you get continuously hydrogen evaluation. It doesn't give anything on the right side, in the anodic side, it gives only hydrogen. We measure by GC mass, is hydrogen, pakka. Then why it is happening? Because here nickel 2 goes to nickel 3, 4. Why it is not going nickel 3, nickel 4, not water oxidation? Instead you get hydrogen evaluation. That means, again, one has to do computation study, theory. We did not do that. By logic of inorganic chemistry, what we explained when reviewer asked that due to strong hydrogen bonding, the electron density or electron around the nickel get reduced. The nickel amount of electron density drifted from metal side goes to by hydrogen bonding. So nickel center become like electron hungry, like to be prone to be reduced, isn't it? So that's why maybe that gives the reduce easily nickel 2 to nickel 1 and give the water reaction. Again question comes. So nickel 2 may goes to nickel 0 because you are getting hydrogen evaluation. We did control experiment. We did not get any nickel 0. It is always nickel 2. So nickel 2 went to nickel 1 and nickel 1 reduced the proton to hydrogen. But let me tell you, it is not homogeneous. We started with homogeneous, but slowly some electrodeposition happens on the electron. What is that compound? That compound we characterize now. So this is the compound originally in aqueous solution. Now this is the deposited compound we characterize, and this is the actually catalyst that gives the hydrogen evaluation. So what we believe that molybdenum 6 goes to 5 fine, but that remains same even after when you do the experience. But nickel 2 goes to nickel 1 and nickel 1 reduce water and come back to nickel 2 and make the cycle. So I'd like to draw your attention that this compound is the material what is deposited, and it is also not anymore MO3. It is a MO3 but molybdenum bronze. It is now mixed valence, and the compound was color was different. Now became very shiny lustrous color. So it is a molybdenum bronze but intercalating nickel aqua hydroxy compound. This is the compound we characterized by different studies. It took 6 months to characterize because we don't get single crystal structure of this compound, the deposited material. Then we did the all sorts of characterization, and we could do the all parameters. Once you got nickel, why not cobalt? So cobalt also we did that. Same structure you got. We thought same thing happening, like cobalt. In this case also pH comes down. That means inorganic acid. But then the electrode deposited material, we get hydrogen evaluation. So plenty continuous hydrogen. It is a better catalyst than earlier one. Then to find out why it is so good catalyst, when we found out the material, it is not anymore just mononuclear, cobalt compound. It is become to cobalt hydroxide. That means cobalt hydroxide and that to beta hydroxide intercalated between the MO3, and that is the now catalyst for HER, hydrogen evaluation. Now you may ask me few things. We are doing electrocatalysis in the low pH, no? pH 3.84. I told inorganic acid. And that making cobalt hydroxide. This is not very surprising. To get cobalt hydroxide, you have to take cobalt salt and you have to make NaOH or KOH. Then you get cobalt hydroxide. Again, cobalt hydroxide two types, alpha and beta. Alpha is more expanded, beta is little compressed. The extended structure. In this case, we get beta. Makes sense because it is in the intercalated. You may ask me, maybe that if it is beta form, it will come out physical mixture. The beta hydroxide and MO3 they are side by side. It is intercalated. We take by px side because 2 theta angle will shift the lower side if it is intercalated. So that way we proved even in the acidic medium you can generate beta cobalt hydroxide intercalated. It is also molybdenum bronze now because some of the MO in the reduced state and is a very shiny color lustrous. If you continuous hydrogen evaluation day and day, week and week, nothing happened. Once it deposited on the electrode. So this single crystal of the parent compound like that, again it is triclinic system like nickel 1, and in this case also the asymmetric unit I am showing here in the thermal plot, and this is the other integration compound. So I again tell you that very surprising that cobalt chloride, if you take from the bottle, it will give water oxidation OER, but in your case when it is in the layer, it becomes molybdenum bronze, it gives hydrogen HER. And these are the parameters. Okay, I have almost reached my last part of my talk. So far, I told you about heterogeneous catalysis. Even the compound was soluble earlier case, but it become deposited, it become heterogeneous finally. Now I'm telling you very interesting supramolecular chemistry. Again, lot of help from single crystal crystallography. Water soluble and homogeneous electrocatalysis. What we did, very simple. We synthesized this compound, cobalt, aqua compound, and this Soft-Oxometalates decaphenate and mixed valent cation also. This is not mixed valent, I mean mixed cation. Cobalt gives 4 plus charge and potassium gives 2 plus 6 and gives 6 minus charge because decaphenate is the 6 minus charge. So this compound as such you can synthesize. In fact, you will buy from already. This is so stable. It is very important compound because biologically active compound. Okay. What is this? The same thing I told you, cobalt hexachloroCO2 dot 6H2O. So these two compounds, as if I put in a crystal, no? So you may this compound if you put in water, it gives homogeneous water oxidation. If it is really true and that too homogeneous, then why you have to make this? You take sodium decaphenate, you take cobalt chloride and put in this proportion, you should get continuous oxygen. Doesn't come. That is the beauty of supramolecular chemistry. Why? When you solve the crystal structure, we found very interesting hydrogen bonding network between this cobalt aqua and decaphenate. Not only that, we took the mass spectrum of that. Okay, and same mass is getting maintained. What I mean is that whatever species we find, no same mass we got. We believe that the compound there in the solid state, when we dissolve in the water, it is remaining the same hydrogen bonded structure. That is why a synergy get established, and this gives continuous water oxidation. So the synergy between cobalt and cluster by hydrogen bonding very important. What I mean? Again, let me tell you, maybe you missed it. I am telling this compound of single crystal structure. If you see the structure, you have cobalt aqua compound, which is like that. You have decaphenylated cluster. That means if you mix them, they should give water oxidation, but they don't give. Only the compound we got single crystal that we dissolve, that give water oxidation. That means the crystal structure is maintained in the solution, and that give the water oxidation. So these are the crystal parameters. I just took it from there, and then we did a lot of study, Raman and already crystallography, PXRD, telling that everything fine. Only thing we proved that whatever solid state is there in solution remaining same hydrogen bonded structure, we check by mass spectroscopy. Then we did the electrocatalysis. I will not go through all these details because that's I want to take out, but I forgot to take out. We wanted to tell you a synergy between cobalt and decaphenylated established, and that synergy gives this job. Now question is that why synergy happen, how it happened, they like to tell you. Okay, so a compound because in this case, sorry, I'll take just almost done. No? Let me go back to here because this system, when I explain anywhere, just to confuse that I'm telling you again and again that this compound doesn't give water reduction, this compound doesn't give water reduction. In fact, you already know this compound, if you take this, it gives water oxidation. I told you already some time back, for some time, the cobalt oxide form. This can give, in principle, can give water reduction, I mean hydrogen. Because vanadium 5 goes to vanadium 1 and give hydrogen. We check, doesn't give. The whole this compound give. But is again, there is no coordinate covalent bond, no covalent bond, only hydrogen bond. Okay? The hydrogen bond. Hydrogen bonding I am showing here. Now, a system, if you want to give hydrogen evaluation, something has to be reduced, either cobalt, 2 has to go to cobalt 1 or cobalt 0, whatever it is, or decaphenylated has to be reduced, vanadium 6 to 5, then they can reduce the proton to hydrogen. As such, they are not giving, separate they are not giving. Even physical mixture is not giving. If we mixture, physical mixture not giving. So what we did, we wanted to know what is the active site. Then we took the help of, okay, these are all, in another, I tell you that one trademark that any homogeneous electrocatalysis, you have to check that make sure there is no deposition happening. I told you many times, if you start with homogeneous, then after some time it gets deposited, and then finally that is the catalyst. Homogeneous electrocatalysis means you have to do after 100 cycle, 500 cycle. Again, you check the surface by microscopy, it will be same. There is no deposition. So that we also did to prove it is homogeneous. Electrocatalysis. Homogeneous is very rarely happen. That's why the maximum case it get deposited. Then I went to my colleague who does computation to know that actually what is the active site, cobalt or vanadium. Vanadium 5 can go vanadium 4, cobalt 2. So we requested do some calculation. Calculation shows very interesting. I am not I don't do computation. Qualitatively, I understood from my collaborator. My colleague student actually did that. My colleague student did that. So this is the homo-LUMO gap of the cluster. Okay. Now cobalt 2 will have two spin state. Cobalt, alpha state, beta state. Beta state gap is smaller than the alpha state. And if you see that now our compound, the compound we got single crystal. For alpha state, this is the gap, and for beta state, beta spin, this is the, that means beta spin is the better, synergy established when you get this. They talk each other because vanadium cluster and cobalt system talk each other. A synergy established, then only it happens. Now, how it happens, I like to tell you. Electron, electrochemistry, machine will give some electron. The electron will be taken by what? Cluster will be taken first or cobalt will take it first, that we want to know. Now we see that LUMO is delocalized here and SUMO SOMA means single occupied, molecular orbital. So we found that in the case of, cluster, the LUMO is electronegativity occupied line with the vanadium cluster. That means when machine give electron, the vanadium will first reduce. And we believe that electron goes to cobalt. Cobalt 2 become cobalt 1, and then cobalt 1 reduces the water to hydrogen. This is, from the, theory. So that means synergy definitely established, because as such, I told you, as such compound doesn't give water reduction, as such cobalt doesn't give water reduction, even physical mixture doesn't give. That means physical mixture doesn't establish synergy, because hydrogen bonding establishes the synergy, and finally we can get hydrogen. So electron come from cluster to, from machine to cluster, cluster to cobalt, cobalt to water. This will get continuous hydrogen. So this is the thing I want to tell you, that polyoxometalates, oxometalates, you can understand first of all. If you are lucky, you get single crystal, you know what is the system. You know the system, you apply your mind and do interesting chemistry. So we found that is a cobalt 2, you can go to cobalt 3, but many times interesting happen. When intercalated cobalt aqua compound as such give water oxidation, if you are intercalated, it is not giving you hydrogen. That means how powerful is supramolecular chemistry, hydrogen bonding interaction. That MO3, electron drifting happen from the metal side, becoming electron hungry. That's why like we reduce, giving hydrogen. As such, cobalt chloride giving oxygen. So a lot of things can be, understood if you have, lucky that you get a single crystal structure. You understand first from the structure, and you can do the chemistry. Thank you so much for your attention. Please.
So now we would like to move on to our question answering session. So yeah.
Hello. Very nice talk, sir. I have few questions, actually, few query, you can say. For your HER and OER part, actually, I have seen that you have mentioned the value of overpotential is around, it's really, really high. For OER, it's around, I think, for MOF 199, it's around 719 millivolt. And for cobalt cases, HER, it was around 365. So it's quite high. So how we can control this kind of
MOP case,
overpotentials?
I can tell you, the MOP, I did not show you some result. The MOP problem is that neutral femur. We got even the first paper, no, 700 something. Neutral femur, we believe the same thing reviewer asked also. They only answered, because the MOP is, neutral type of femur. If you can manage to put inside some conductive, electro carrier, you can improve. One paper we published in inorganic chemistry after some time. After that paper, we put one Kagan as electron carrier inside. So that 700 something went down to 465. So because of the neutral nature of the MOP, high, overpotential, we could not improve unless you put some inside electron. That can be done. So it is what we understood. If you can manage to put some conductive material inside, you can improve the overpotential.
Yes,
and in the case of intercalation, we always good. We get always within 300 millivolt overpotential, because that problem is not that high. They're in the conductive nature. It is not that like a neutral femur. No? And in fact, that molybdenum now reduced. Molybdenum bronze happening. No, so that helped to make the overpotential less.
Yes, sir. And one question more, actually. In one of your slide, I have seen that you are using cobalt, I think cobalt chloride and like things, and in an intermediate, beta cobalt hydroxide is forming. So how you confirm that in your reaction media? Beta hydroxide is forming?
Yes. We also thought it's a beta mononuclear cobalt compound like nickel.
Yes,
nickel case is a mononuclear, 5 water coordinate and 1 hydroxy. So when we got the deposition, this is a lustrous compound, fine, very shiny material. When we took, now we always make more compound on that. We take and we send for XPS, we send for all sorts of study. For T TEM, the from Flint's gap, we could it was definitely not mononuclear we found out. Mononuclear is a characteristic electron spectrum also. Then we found out it is a cobalt hydroxide. We also didn't believe first because being in the low pH 3.84. But then, if you think the basic inorganic chemistry, in that in that cathodic potential, when it's going, that condensation happens, and that's why it is forming. And then we found out it is cobalt, from the TM study, it is cobalt hydroxide, but then alpha or beta. Then we found it is beta from the exact, that gap. Interesting thing is, this also makes sense why it is beta, because first we thought it is a physical mixture, that maybe beta cobalt hydroxide form, cobalt hydroxide and MO3 side by side. But then it was intercalated because PXRD that we identified 002 peak, that is shifting left side. Okay. So, and beta is the compressed one and alpha is the elongated one. And because it is the intercalated in nature, that's why maybe it is beta form actually. So, TM study help and other two study help from exactly Raman, little different from the alpha and beta. So, that we take out from there and we did rigorous study. Actually, it took a lot of time to characterize this compound. And it is now mixed valent compound also. It is a molecular reduce. But that doesn't matter. That doesn't give hydrogen, only that cobalt. And another interesting thing is cobalt beta hydroxide also known from, if you put cobalt chloride and then add on the sodium hydroxide, you get beta. Two ways you can put. Zeolite Y supported cobalt hydroxide, we made alpha that give water, oxidation. Beta also give water oxidation photocatalytic. For the PK Datta shown from, Ohio State University. But this same beta hydroxide giving hydrogen evaporation. So it's very, confused. Then we realize because the compressed nature and electrons, again electron drifting from the metal side, instead of oxidation, it got reduced. So definitely cobalt 2 goes to cobalt 1 and that does. But they never goes to cobalt 0 by the way. That is, people may think not cobalt 0 easily give hydrogen, but we never saw. We did a lot of control experiment, we sent sample for XPS, we never got cobalt 0, either cobalt 2 and cobalt 3 in the case of gold.
Yes, sir. Thank you so much, sir.
Have we got any more questions here?
Good evening, sir. So my question is that in one of the slides you showed that the window aperture of the host structure, that is ZIF8, it was written that the window aperture is smaller than the Kagan structure. So is that the window aperture it represents the whole cavity hole of the ZIF8 structure, that is the host?
I'm telling you, ZIP8 internal cavity diameter is 11.2 to 3 angstrom. Okay, and whatever compound we use from one end to another 10.8 angstrom. It is not easy to encapsulate inside unless you do in situ, because ZIP is formed by organic ligand and zinc chloride. So that you put, and your MOP already, your POM you already keep, or the POM, the POM cluster, Soft-Oxometalates cluster, you already synthesize, keep in the in situ. So when MOP is forming, is taking inside the cavity. Once it inside that, it cannot come out because no aperture, no window. But only problem is we don't understand the loading level. Some cases you get 1 cluster per 7 kg, some cases you get 2 clusters per 7 kg. The loading level, so far we didn't understand. Even if we put more also, but one way is good. Full loading level is not good because electron transfer will not be facile. So anywhere you have to get the full, electron transfer facile, then only you can get all this, reaction. So the low loading level is good, what we got. But why it is happening just like that without our control, that we don't understand.
And so one more question, sir. If the point was written that window aperture of ZIF8 is smaller than the Kagan, smaller than the Kagan structure. That means Kagan structure is bigger in size than the ZIF8.
That's why I'm telling you. That's why once you form in situ inside, it cannot come out. It's entrapped like sheep in a bottle. In situ means what? Tell me. I am putting zinc-2 and organic ligand, 2-imidazole ligand. These two form the MOP will form with big cavity. Forget about small aperture, window. Now, our compounds already there. We already put the compound in the medium. So, what is forming the MOP is picking from the solution and putting inside. So, aperture may be small, no problem. It is small good for us, it will not come out. We have one more paper I did not tell you. Let's say cobalt aqua compound, we can do with zeolite. Zeolite, why you know that? 13 angstrom super cage and window 7 angstrom. Okay, cobalt aqua compound 1 into 1 and 4.5 angstrom. There, if you put inside, it comes out because window is 7 angstrom. Even inside 13 angstrom cage, cobalt mononuclear compound inside, you put the KOH or NaOH, cobalt aqua compound come out and hydroxide a layer from on film form on the surface. That's why the aperture is very important. In that case, aperture small, window small, so it cannot come. So you have to put in situ, then only get inserted. Yeah.
Okay, thank you, sir.
Any more?
Any more questions? If not, then we would have a small announcement. So please proceed.
Please join me in welcoming Professor Tariq Hasan to the stage to present the token of appreciation on behalf of GIAN Force and ISER Kolkata to Professor Samar Kumar. Have a and Professor Roy, you can also.
Oh, that is there. I'll help you.
Okay, you help me.
It's like that.
Nice.
Mhm.
Very good. Very good.
Thank you. Thank you. We have photo together. We have. Thank you.
Good.
Thank you so much.
Thank you.
Thank you, Professor.
Turn it.
So now we can go ahead to the lecture of Professor Rahul Banerjee, sir, from Department of Chemical Science. Thank you.
Good afternoon, everyone. So now we have our next speaker, Professor Rahul Banerjee. So Professor Banerjee does not need any introduction, and he also said he does not need an introduction to the audience. So he is a prolific productive scientist, and his areas of research are carbon capture, covalent organic frameworks and all. And he's another thing is he's also associate editor of the Journal of the American Chemical Society. So with this, I request Rahul to start his lecture. Thank you.
Very good afternoon to all. And of all, thanks Mujit for inviting me. But me, he's not there, no? Okay. Yes. Okay. Huh? No, I think it's okay. Thank you. So thank you, Somujit, for this opportunity, and I will talk about porous material. I work on porous materials. I have been working on porous materials for quite some time. So therefore, I'll talk about porous material more or less. All right. So what are we talking about? What is a porous material, and why should we care about it? I mean, eventually, whenever I know that most of you, and also I tell this thing to my students. So let's start it a little bit lightly. Whenever my group, we are doing a group meeting. So, and some of my students are also there and absolutely have no, I mean, anyway, so they can vouch for it. So, so whenever I do a group meeting or we do a group meeting, so I tell my, so they're giving presentations and they're doing quite a bit of work and very beautiful work, to be very honest. So I say that, this work someone has done, that work that person has done. What is the point, who cares about this kind of research? So eventually one of them told one day that, why don't you tell which is the good one? So then I said, look, there is a point. What is the point? My PhD is over. First point. Second, I got a job. Third, okay, I also have a house. Therefore, my job of generating idea is those days are over. Now it is your job to generating ideas, and my job is to criticize them. Like a coach says, "Na, aisa karo, aisa karo, aisa karo." So therefore, so what is the point at the end of the day when we are doing research? So that's very important to think. As I said, when I was like you, my first primary focus was to get a job. Number two, get married. Number three, get a house. May not be in that order, but whatever it is. So maybe two comes first or one comes second or whatever it is. So may not be in that order, but it was like that. But eventually now the time is not same. I did my PhD almost 20 years ago. Yeah, almost 20 years ago from Central University, Hyderabad. So Professor Samor Das, interestingly, Professor Samor Das and myself, we joined on the same day. So he joined as an assistant professor or lecturer does this, and I joined as a PhD student. Anyway, so we also had the similar things, but time has changed. In 20 years, time has changed. Things are tough. Things are not so easy at the moment. Many people are doing PhD. Jobs are not that much, available. So tactically, at the end of the day, we must try to convince to the world that why are we doing this particular research. That's very important. Please ask this question as soon as and when you are doing it. So what we are trying to do at the moment, and I received some amount of money from the government, and also we are trying to see if we can change it into biomaterials, but that's a different thing. We are trying to, doing some kind of CO2 capture, some kind of the other. But CO2 capture is not that much, CO2 capture, we can say, a lot of people say that CO2 capture, CO2 absorption, so on and so forth, MOFs will do this, that, blah, 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 whatever. But CO2 capture in a way, the challenge is that whenever you are trying to do a capture, first of all, there are pressure involved. CO2 is coming, right? CO2. And the amount. Now, let me give you a essence of the amount. So, I visited Tata Steel some times ago, and Tata Steel produces 20 million tons of steel per year. 20 million tons of steel per year. Each ton of steel produces 2.5 times CO2. So, each ton of steel produces 2.5 tons of CO2, which means each year Tata Steel produces 50 million tons of CO2. 50 million. 1 million is 10 lakhs. So 50 into 10 lakhs tons of CO2. Okay.
So now you know how much CO2 they are producing. So if you want to produce a capture, or if you want to create a capture agent which will capture that amount of CO2, first counter question will come, what am I supposed to do with that CO2? It's an obvious question, no? What am I supposed to do with the CO2? So even that problem we could not ascertain. First problem people are trying to say that, okay, first at least capturing some way or the other. Capture के बाद देखेंगे what are we supposed to do with it. So these are the things, and lot of people there at the moment using amine based adsorbents. So I don't know whether Kari has spoken about it or not, but so there are many ways to do it. Amine based adsorbents are one of them. If you have recently seen Professor Yagi's paper on Nature, so they are trying to do direct air capture and other things using the amine based adsorbents. So amines will form carbamate will precipitate, and then you can take the precipitate, heat it up, and you get the amine back and you get the CO2 back. What do I do with the CO2? I react that CO2 with calcium oxide, produces calcium carbonate, which is basically lime. And then that lime, we take it and put it inside the cement. With that cement, we will construct it. So that is sort of way, but there are a lot of issues. Anyway, so these amine adsorbents are required, and these are the adsorbents that we need. So we are working on such kind of porous material, and so these in an image, I'm sure you have seen it. So this image I have copied from Professor Shivram's talk, where he has shown this very beautiful image. You are not there. Actually, it looks like an iceberg. It is not. So it's actually a plastic bag. And this was a very important image, and it won lot of prizes, lots of prizes. And I also checked in Google that unbelievable number of prizes this image has won. So now the point is, how do I use these materials? How do I recycle it? Produce these MOF materials, and then use that for that matter, or porous material, and use that for that matter to absorb CO2. So how do I do all these things? How do I work it out? Okay. So the way to do it, so first let us understand a little bit about porous material. I speak about maybe give and take 20 minutes, 25 minutes, so that we can discuss more. So porous materials are the materials that we see in the literature a lot, or we are encountering porous materials. If these things are whatever you are wearing, these are all porous material. You soak it into water, they will become heavy, right? And then so on. And you dry it, they will become light. So these are different porous materials that you have seen. I mean, I don't know if you have noticed, many years ago, my grandfather, when he was having the morning tea, so what he used to do is he will not drink the tea in a way. So what he used to do is that he will take a couple of biscuits, and then he will dip those biscuits on the tea, and then lift the biscuit, and then have it, and so on and so forth. So keep on doing it, and eventually the tea is gone. Okay. So this is the same way we are planning to also do the CO2 capture from that. So these are the porous materials we are talking about. Now, how do I construct a porous material in the laboratory? If I ask you to do that, like we are talking about now, ZIF8. ZIF is ZIF. I don't know whether you were paying attention to the last talk. I'm sure you were. ZIF is the term called zeolitic imidazolate framework. Today I don't have time. Otherwise, I would have explained why it is zeolitic, why it is imidazolate, and why it is a framework. But anyway, so the way to design a porous material is that you take a joint, you connect that joint with another joint with a strut. If you are having difficulty to understand what do I mean is the following. Let's put it in this way. All of you have seen bamboo rods? No. Right. When they are lying around, they mean really nothing. I mean, the word bamboo means something in life, but that let us keep it aside for the time being. But at the moment, Kari will probably not understand that joke. So so it means for Indian perspective, it will mean a lot. I mean, anyway, so they are lying around. So they mean nothing. Do they mean anything, to be very honest? No, they mean nothing. But if you can erect them, and you can construct, and if you can stitch them up, then they mean something. And that is the goal, and that is the target. So Many times I have gone and given a presentation on these metal organic frameworks or the porous materials, and people say, hey, kya hai? What kind of garbage is this? Zeolites are there, sand is there, this is there, that is there, carbon is there. But what I'm trying to say is, if you keep aside those points, if you just take the idea that when you have absolutely meaningless substance, but you bring it together and you stitch it and you create a story out of it, even if it doesn't do any job, let's put it in this way, even if it does nothing, lots of people, there are a lot of companies and all based on MOF and all, I'm not going into it, but even if it doesn't, but the concept itself is beautiful. In my class I do teach sometimes, I don't know whether you heard or not, there is a term called quasi crystal. What is a quasi crystal? Quasi crystal is in mathematically, those who are in the crystallography, if you are learning crystallography, mathematically 5-fold symmetry is impossible. In a periodic structure, 5-fold symmetry is impossible mathematically. You can Google search it. 5-fold, it can be 1-fold, it can be 2-fold, it can be 3-fold, it can be 4-fold, and it can be 6-fold. Okay, 5-fold is impossible mathematically. However, a gentleman named Dan Schussman, he actually found out that 5-fold symmetry, and in the crystal, and he named it as a quasi crystal. Now, when he named this quasi crystal and all, he published the paper and all these things, he was ridiculed a lot, especially by Linus Pauling, the great Pauling, probably one of the finest scientists of this century, So great Pauling ridiculed him a lot. He said that, you please check it in Wikipedia, that there is nothing called quasi crystal. There is only something called quasi scientist. Only something called quasi scientist. So he was ridiculed like that. So Simin, that's what I'm trying to say, that without, if you believe something is interesting, I would recommend that you pursue it, with that belief. So this is the beauty of this material. So these sticks or these things, you stitch it and you can create a lot of beautiful architecture where you can host a lot of things. So this is called a metal organ. On that concept, this concept of metal organic framework or the reticular chemistry came into the picture, where once again you take a joint and then connect this to another joint via some kind of organic strand. So this is what we have taken is, this is terephthalate. I talked to you about that plastic, that plastic bottle that you are using over there. So this is made of polyethylene terephthalate, PET bottle. PET means polyethylene terephthalate. So the ingredient of this is terephthalic acid based polymer. So you take that terephthalic acid, which is there in the plastic, and you can synthesize this metal organic framework form. Okay. So so this is reaction of this terephthalic acid and zinc nitrate. You produce these beautiful crystals. They will precipitate, and you can get a lot of you can. This is the crystal structure, of course. This is the and crystallography. Since it is a crystallography course, so this is the crystal structure. This yellow ball actually represents the openness of the structure, the void, the vacant spaces. How do I make this MOF? These are called MOF, by the way. Why MOF? MOF. MOF. Why MOF? M means metal. There is a metal, zinc. O means organic. There is organic. Okay, organic is the terephthalic acid, and F is framework. So MOF, or metal organic framework. Okay, all right. So this was invented by Professor Omar Yagi, for which there is many people are expecting that he will, in sooner or than the later, he will receive a coveted prize. All right. Now coming back to it, when I was working with him, when I was a postdoc, almost 17, 18 years ago. So that time we used to take, and it was the beauty of it, you used to take one organic linker, you react with one metal, you make one metal organic framework. You take another organic linker and you react with another metal, you make another metal organic framework. You take another one, and so on and so forth. You can keep on doing it, and you can make thousands and thousands of metal organic frameworks. Thousands. As I said, these metal organic frameworks are empty. They are like that sponge or the cake I have shown in the beginning. So it's empty. In the space you can put things. In this particular case, CO2 or hydrogen or methane or other things. So you can do a lot of beautiful chemistry in that. How does it work? How does it absorb? I don't know whether this video will work or not. I am not very sure. Most likely it won't. Oh, okay, it does. Okay. So this is we did when I was a postdoc. We did this video for the BASF. It is still there in the YouTube. So this is the SEM image of this metal organic framework. And where if you just take one crystal, it will look somewhat like this. One crystal. Crystal means lattice plus motif. So these are the motifs. They are organized and formed a beautiful long lattice. You absorb, allow it to absorb, allow the gas molecules to absorb. They will come in and they will go inside the MOF and remain stable there. So this is called the gas adsorption, adsorption, AD. There is something called absorption as well. So what is adsorption or absorption? Ad means AD. So let's put it in this way. Adsorption is on the surface. Absorption is inside. So let's put it in this way. When you are eating a cake, that is absorption. When in your birthday, your friends take that cake and put it on your face, that is adsorption. Okay. So ad and ab. So you understood this. Okay. All right. So how does it work in reality? In reality, when you have these MOF, which are powders, put inside a canister, empty canister, and then you pressurize the gas, you will be able to absorb much more than, let's say, 3, 7, 10 times of gas absorption. Now here is a counter question. I am assuming that many of you do have cooking gas in your house. Okay, all right. Harry, once again, we are not still as developed like you. So we have cooking gases in our houses. It's not that you switch on the oven and it is all hot and everything is fine. So anyway, now we have cooking gases, right? How long it lasts? Month and a half, max to max 2 months. I seriously doubt it goes more than 2 months. Okay. Why? Why 2 months? Why not 12? Why not 24? Why? The reason is when you are storing that gas, you are storing it as not as a gas. You are storing it as a liquid. Then you are giving a pressure by, and that pressure, so you are releasing the pressure and you are using it as a gas. So that's the beauty of this material. So release of this pressure. So from the stored something, when you are talking about storing the gas as a liquid, that means you have to pressurize it. When you pressurize, they will give back pressure. You have to sustain the back pressure. If you want to pressurize more, they will give more back pressure and so on. So your wall thickness of your cylinder will become thicker and thicker and thicker, and eventually it will form, it will be so heavy you can't lift it. Why is it so? How do I take a solid powder, like a powder material, put it into a cylinder, and I'm saying that I will put some gas molecules or some gas, and it will take up more gas. How exactly it will happen? The way it happens in a very simple manner, if you understand. So when we have the gas molecules, let's say these are my gas molecules. So then this will assemble on, in terms of what the Brownian motion, this will assemble on the wall of these cylinders. If you entangle the wall, make it a bit larger, then you can have many more gas molecules. So you increase the surface and you have more adsorption, or surface absorption. So now, when we are taking it out, these gas molecules, suppose if I take it out and put it in a flat surface, I will probably get a surface area. This is called surface area. So let's assume it is 1 meter by 1 meter. So it is 1 meter square. Okay. So that is the surface area. Like we, whenever we are purchasing a flat, we say carpet area, super build, those kind of things we say, and then we check it out, what is the price of that per square foot, etc., etc. And we very proudly say that, per square foot it was 10,000 rupees or something, so something like that. And I bought 2,000 square foot flat, something. So what I'm trying to say is, so this is the surface. Now this is the surface area. Now how do I quantify the surface area with respect to the solid that I'm putting in? The way to do it is that, let's say I'm putting sand, I'm increasing more surface area into the system. So it will absorb also on the surface of the wall, and also on top of that sand particles as well, because that's also a surface, right? Initially it was empty, now some sand is there, so more amount of species will come in. Okay, so this is one thing. Now second is, if you take it out and once again flatten it, let's say it is 10 meter by 10 meter, so which means 100 meters square. Suppose I have added 1 gram of sand, so it is 100 meters square per gram. So that is the way you measure the surface. Let's say I have mock molecules, mock particles now. Instead of only on the only at the surface of these mock particles, now I have an opportunity to put gas molecules inside as well, like in the video I showed. And this time I can have 100 by 100, which means 10,000 meters square per gram surface area. That is the beauty of these materials, where we had a metal, we had an organic linker, they were meaning nothing, but eventually they come together and form something very beautiful and very productive for that matter. How do I really measure the surface area? In a way, the way I measure the surface area is, suppose if I ask one of you that all of us will go outside and I want to know how many chairs are inside. You cannot look into there and you cannot count. From outside itself, you have to tell me how many chairs are there, unless you look into the board where it is written how many chairs are there. So you have to tell. How do you do that? The way to do it is that if you let people come in one by one, one by one, one by one, and keep on counting, keep on counting, keep on counting, one fine moment, someone will come, someone will come inside and then go out and then will tell that there are no chairs. I mean, what am I supposed to do? Sit on the floor? So then you know the number, and that precisely you do when you are measuring the surface area, that you dose the gas molecule one after another, and you do Boyle's law, P1 V1 equals to P2 V2, and then you measure the pressure drop, and from there you back up. So that is the way you measure the surface area. Next time if you are working on any porous material, please make sure that this curve looks like this. More it goes higher in the zero, then your material is good. As simple as that. Good means it is useful. It's not that not useful when it is lower, but more is always better. Okay, so coming back to the point now, there are other porous materials that we do encounter. For example, I don't know if you are using AquaGuard or Kent or something in your house. I'm sure many of you are doing it. So there are some things called ironil, or which will filter the particles. There are so much iron. If you just walk through this corridor, you will see that there are these water jets which were supposed to be used if there are some fire or something like that. If you just go, you will see that next to the ACM room there is a water jet, and there is no water at the moment. There is little bit of leakage, and through the leakage, when the drip has happened, you will see it is full of iron particles. You just go and see. It is red colored water. The water is like red color. You can go and see it right now. Okay, so that means there are a lot of iron. How to stop that iron to going into the water and eventually to our stomach? So you use something called ironil, so an iron filter, where you have similar kind of porous materials like silica, and where it will just protect or block these iron particles to come in. It will absorb those iron particles on the surface so that it will not come inside your iron filter, or inside your AquaGuard. Most materials can do much more better job, because these things do have a limitation in terms of their surface area, where the MOF is at your disposal. Whatever you will make, you want to make high surface area MOF, you can make it. Low surface area MOF, you can make it. It's up to you. Now coming back to the usage of it. Now obviously I asked now this point that what is the usage of this material. So this is something I want to show it to you. This is CNG vehicles. CNG is compressed natural gas. There are CNG vehicles in the moment. I'm assuming that it will be taken over by EVs, but CNG vehicles means where in the tank you have where you have the methane, it is stored around 200. So I will tell you 200 milligram of methane in a way per gram of the tank. It is stored in this particular way. So 200 milligram. So in this particular way, if you have to store the methane, then the pressure that you have to give is 200 bar. This is 1 bar. You have to give 200 bar to store it in that condition, that methane, which you use, okay, CNG cars. So at the moment, they are trying to use this kind of different kind of adsorbent. This is porous carbon, by the way. These are porous carbon blocks, and this is the target. It should be 300 cc per gram, okay, and it is volume by volume, and or let's put it in this way, 0.5 gram per gram. If you are using an adsorbent, if you are using 1 gram of adsorbent, it should be able to take 500 milligram of methane, period, with a reasonable pressure. So this is the target that at the moment Gas Authority of India Limited has set, and then many cars they are trying to work that thing out. So this is the target at the moment, and MOF materials, they have tried to use this. This is the MOF material. In case you are trying to think that what are these MOF materials or not, please go to BLD or Sigma Aldrich, and you can purchase this compound called basolite. Basolite is MOF. All the MOFs that has been commercialized, you can purchase all these MOFs from market if you really want. But if you want to make it, it's even easier than purchasing. So this is the BASF car loaded with this basolite MOF, and this has started from Berlin and finished probably in finished in Bangkok. So they did this run of this BASF car. Okay, so now coming back to this drawback of these MOF materials, there are some issues of these MOF materials as well. The problem of this MOF material is that these materials in general are not stable in water. In general, they are not stable. So, I give this analogy. I think many of you have heard my giving analogy. So I told, now this is porous material, this is porous material, right? Whatever you guys are all wearing, all porous materials, right? I told. So imagine it is not water stable. It will dissolve in water or something like that. It is unstable or decompose in water. And you go outside and there is a huge rain and you have no umbrella. So imagine what will happen. So that is not advisable. So you need a stable material at the end of the day. So that on that note, when I started working with the industry since I came back, I was in CSIR at some point of my career. So there was a pressure to work with the industries and all, and industries, they will come and ask these kind of questions. What are the questions? First question is your material cheap? This is porous material, right? This is also porous material. Imagine each of these porous material is, let's say, 1 crore rupees. How many of us can afford this porous material? None of us. So what will be our scenario? We have to go to only that person who has given his son's marriage for 5,000 crore can only get this 5,000 of these things. We can't. So they will first ask these questions. If you are planning to work in an industry, these are the questions you have to address. Is this cheap? First. Second, can I make it in bulk? If I can't produce in bulk, if I produce one of these porous material, let's say per year, then it is not going to work. Can I make it in bulk? Fast, rapid. So these are the questions that we have to address. Not that overnight we will be able to address everything, but some of these questions you need to try to address. So on that note, when I started, when I was a postdoc, that time my postdoc supervisor was working on this, and then I came back. I'll tell you what exactly we did. So first, what we did is, so this is the material. Now let me tell you. So what he told is that, look, these MOF materials do have some problem and all. We should be a bit forward thinking, and we should discard the metal. So how to discard the metal? So there should be same MOF but no metal involved into it. So what he did is, that time he took this amine and aldehyde, and actually he didn't do with the amine and aldehyde, it was with boronic acid, boronic ester, but I will show it to you. So the concept was, if you take a symmetrical organic building block and another symmetrical, this is C3 and this is C2 symmetry, they will, if you draw it in a piece of paper, they will look like this hexagonal thing. You put it into, once again, still I have not synthesized anything in the lab. This is just a design in a piece of paper, and you will make these porous structures. Just look at this picture. This is drawing. There is no synthesis in the lab. Just drawing itself tells me that there will be porosity into it. Okay. So now afterwards, you can synthesize in the lab and all, you can crystallize it as well. Now the problem, so these materials are called, as I told you, these materials are completely organic. So organic part is still there. Framework is also there. This is a framework. So OF is there. Only metal gone. है ना? So इनके metal के जगह पे what we got covalent bond. So covalent organic framework. Very simple nomenclature. I mean, science should not be that difficult. So, okay, but the problem is whenever we try to synthesize in the lab, in this particular way, we thought that it will synthesize in this way. I mean, even all of you are there. Are you really coming, sitting in very close? Everybody is scattered everywhere. I mean, they are molecules. They will be like that, scattered everywhere, and eventually produce amorphous garbage, which is of good for nothing. So that was the problem. Now, how to solve the problem? To solve the problem is something called freeze pumped thaw. You don't have to understand the name. If you just hear the name freeze pumped thaw, you can understand that the name itself, has a josh. It has some fire inside the name freeze pumped thaw. The way you do it, my students used to do it. We have been just last night we were discussing about the freeze pumped thaw, and I said that if you are planning to do it here, you must be super careful about it. Anyway, so how to do it? First, you take the high boiling solvent, and inside you add all the ingredients that you are planning to add, or that you are doing these ingredients, amine and aldehyde, and then make a solution. Then put the solution inside liquid nitrogen. Take that liquid nitrogen frozen thing and use a blowtorch on the top to flame seal it. Before you do the flame seal, you must make sure that you do a high vacuum. Now, when you are doing high vacuum, it is frozen already, so this top part will be evacuated. Now, there is a counter question. When it is top part is evacuated, and then if I flame seal, will not some accident happen? I'm using a blowtorch, by the way. Of course, there will be accident. So you have to be very, very careful about it. And you are using a thing which may anytime catch fire if you are not careful. Okay. So once you do that, then the job is not done. Then you take that and put it inside oven at 120 degrees centigrade temperature for 7 days. So what will happen? 120 degrees centigrade temperature. Now this will try to go out, evaporate. It can't because it is flame sealed. So it will give back pressure. Now what is the problem? It will give back pressure. So at higher temperature, solubility increases. As you increase the temperature, solubility increases. At higher pressure, solubility decreases. So in this process of tug of war, you will eventually make this thermodynamic structure we are talking about in, if you are lucky, on a very lucky day, 50 to 100 milligrams. If you are super lucky, we are talking about 50 million tons of CO2 to scrub. 50 million tons. We are making in 7 days 100 milligrams. If you are lucky, please take a piece of paper and assume that this is, let's say, ton by ton. 1 ton of CO2 will be captured by 1 ton of MOF. Let's say you now do a back calculation and you tell me how many days it will require to capture all the CO2 that Tata Steel is producing in 1 year. Just do a back calculation and you will get how many days it will take. One lifetime, our lifetime, our children's lifetime, their children's lifetime, and their children's lifetime will go, but that Tata Steel 50 million ton, that pipe will never fill. The problem. So that's why the production is important. So in order to get the production thing sorted and to get this thingy, make it in bulk, not this garbage, what we are talking about, what we started to make is the following. We adopted a different strategy. And this strategy, I will very quickly explain. What we thought that, here this reaction is happening too fast. So therefore, let's try to protonate this amine, and then this aldehyde will react much more slower, or it will, the thermodynamic minima will drop a bit, so that this kinetic product and the thermodynamic product will form in a similar rate. Not in thermodynamic, is not the slower rate. So we tried to do that, and we used a organic acid, pyridoxine sulfonic acid, reacted with this amine, made a salt. Now what happened is that when the aldehyde came in, it has to first break that, or deprotonate that amine, and then it can only react. So in this process, it gave us little bit of time overall that for the crystallization, and we felt that it will crystallize. That exactly happened. We took this process, and this process eventually led. So this process is something like that. I don't know how many of you have seen making cakes in your house. So how do we do it? We take flour, then we add egg, add little bit of water, not too much water. Then we whisk it. Why? If you don't whisk, what will happen? That cake will not froth. Okay, so it will not have a foamy, very nice thing. Okay? The same way, the exactly same way you make biscuits as well. Exactly same way. But what is the difference between a cake and a biscuit? Cake is very spongy, right? Whereas the biscuit is much brittle, much brittle. Whereas you are making it in the same, almost same way. So the water content is also very important during this reaction. How you are withdrawing the water, how fast it is, and so on and so forth. So that precisely we did. We added this acid and the amine, made a dough, and afterwards, added a little bit of water, I told you, and made a paste, put it into a preheated oven, and then wait for a few minutes. If you really want to do it fast, you can do it in a minute, but I would rather say give it about 10 to 15 minutes or probably an hour, and then eventually you will make this covalent organic solvent. They had outstanding surface area and all these things, but that's not the point. Following this procedure, as you can see, this is 2017, we published this, and I left NCL on 2017. I joined ICAR Kolkata on 2017, and following our procedure, my colleague Shatabdi Porel Mukherjee and Santosh Babu Sukumaran, they use this twin screw extruder. What is twin screw extruder? I don't know. You are younger, I mean, you people are young kids, so you probably don't know. But when I was a kid, my grandmother used to use something called, we never had ready-made haldi powder, this powder, jeera powder, this powder. Everything used to be made in the home. So she used to use something called a mortar and pestle, that is an Indian mortar and pestle, that is in Bengali mortar and pestle, that is called shilnora. Okay, so that is a traditional. This is just a fancy way of talking about mortar and pestle. Twin screw extruder. Twin screw extruder means one screw goes clockwise, another screw comes counterclockwise. You put your stuff inside and you get the product. That precisely they did. They made it in 1 kg scale for the Gas Authority of India Limited. That's a company. Company will not just give you money and then go. They will come and ask, where is the product? So they made, these are the chips you are talking, you are seeing over here. They are stable in more or less all solvents, which we have already figured out. Anyway, so that more or less what I wanted to say. As I said that it is already 6 o'clock, I mean, touching 6. So I hope that you had a nice time, and in this GIAN course, Somojit is doing a fantastic job. And I hope you have understood this phenomena. But in case you are thinking that what else I can do on this using this material, I'm not talking only about MOFs and COFs, but in general with using porous materials, you can do many things: storage, catalysis, separation, sequestration, many things you can do. Once upon a time, I mean, when I was just a young assistant professor, or I would say scientist at NCL, we had a huge porous material group in the country. Huge. I mean, they used to get huge funding in from industry. Slowly with time, it got dissipated, and there is nobody at the moment. But I would recommend that you look into this research, and you will find a lot of interesting features on it. In case you still are not convinced, at the moment, there are a lot of work is happening on the calcium based, like for example, I'm sure many of your mother especially, or grandmother, they consume this calcium tablet because of the osteoporosis. It is especially for the Indian woman, because of our diet, we suffer from it. My mother is suffering, my mother-in-law is suffering, and so on. It happens. It happens because of our diet and weather. So, and calcium tablets will create indigestion, it will create stomach pain and many problems. Okay. So therefore, a lot of people are saying that we will, instead of using directly this calcium tablet, we will use the calcium ion and react it with amino acids and create this edible MOFs or edible MOF material, and then which we can consume. This is the company there. I mean, I'm not just saying, just throwing some comments over. So this edible MOF based materials, they have a company where they are using it for the skincare products, still not edible, but for the skincare products and stuff. Well, that's more or less what I wanted to discuss. And also these are the group members. This is an old picture taken over there. So Kalipodo has gone to Caltech, Shivani is in Germany now, Madhurima is in Japan, Soikot has joined a company, Ashok will leave for US very soon, and so on. And the other people are, I mean, the way I'm saying, if I do this GAN course I mean, lucky that we are doing this GAN course today. If I would have done this GAN course 1 year later, the way I'm saying, he has gone there, they have gone, I know. In this picture, only I will be standing. Nobody else will stand. Well, with that, these are the other funding agencies, and thank you very much for your patience.
Thank you, Dr. Banerjee, for this amazing session. So I would like to ask the audience if they have any questions.
Good evening, sir. Sir, you said that porous materials are water unstable and other drawbacks. Then how does the porosity influence the mechanical or chemical strength of any materials?
Porosity, if I understood your question properly, so you were, I mean, first of all, MOF materials in general are unstable in water. That is number one. Now, second is in terms of porosity you are talking about. Porosity influences the mechanical strength.
How does the porosity influence the mechanical or chemical strength of any
Chemical
material?
strength in the sense the chemical stability. Chemical strength is chemical stability. So in case if you can, I mean, of course, there are quite a few MOFs present which are very chemically stable. But it's not that all the MOFs are chemically stable, to be very honest. So that's what the challenge at that moment to move towards the covalent organic framework. Now, in terms of mechanical stability, if you are talking about pelletization or I mean, what kind of mechanical stability you are talking about? Are you talking about to make the pelletization when the gas is coming in high pressure?
Any kind of, I mean, with the materials, if we use any kind of physical activities.
So, for example, if you talk about let's say pelletization or the pressure. So there are two ways mechanically things can deform. One is that if you pelletize means like that when you are filling these MOFs into a canister, you must have pellets. Now question is why? Why not powder? Because powder things will have interparticle void. So that is a dead space which you don't want. You want as less dead space as possible. So for that you have to give a pelletization. Of course, you can pelletize, and MOF materials will pelletize. Their surface area will of course drop a bit because now they are condensed in a smaller space. But overall, still it will be good enough for making the pelletized MOF material. Suppose if you take a, let's say 5,000, 6,000 meter square surface area MOF, after pelletization it will probably become 4,000 or something, which is still very good in terms of zeolite and all. And you can utilize it and they will do very fine job for the purpose. So that is the mechanical stability you are talking about. When the gas is coming in, they will also come in with the pressure. Of course, they will come in with the pressure, and that's what the important part about it. But here, the pressure that in which generally the gas comes and hits a adsorbent, it's roughly about 10 bar. It's not that high, because they have to also be careful. If they pressurize it too much, that pipe in which the interaction happens, that might crack. So they also are very careful about that matter as well. So generally when the flow is happening, they will concentrate it in one place, the Tata Steel people, or for that matter any power plant, and then eventually take it and then about 10 bar, 10 to 15 bar, and push it over there. Generally MOF materials and any other solids are stable at about 10 bar, 20 bar. It's not the problem. It's when you are hitting 80 bar and 100 bar, then you are in trouble. So round about 20 to 30 bar, there is no problem whatsoever for any solid for that matter. Even fabric also remains stable around 20 bar. The third point is the recyclability. If you are keep on hitting something for 20 bar pressure for let's say days, then what will happen? That's a correct question. In that case, some amount of amorphization happens. Things start breaking. So this is a aspect that I don't have an answer at the moment, but yes, you are correct that if we keep on doing it for a longer period of time, 5,000 cycles, 50,000 cycles, 500,000 cycles, then it becomes a problem. So some of the materials that at the moment are available, they can stand about 5,000, sorry, about 50 to 100,000 cycles, not 500,000. So that's a challenge. But I'm sure, hopeful that something or the other will happen and it will be worked out.
Thank you so much.
Sir, we see that MOF is used in MRI contrast agent. So we know that gadolinium is used in as MRI contrast agent. So the what is the mechanism behind it? It has a MOF.
In general, the MOFs that has been used in the MRI contrast agent are not porous. So they basically carry the feature of the gadolinium on. In gadolinium based materials, whatever you are using, so suppose gadolinium based salts or something you are using in MRI contrast agent, what people have seen is that if you use it for MRI contrast agent or compared to MOF, and this is my viewpoint to be very honest, when you have a very periodic array of gadolinium, rather than just a random organization of it, then your contrast is much better. That's what has been seen. For that matter, if the porosity is not that much important, it is just has to be very periodic array of gadolinium. That's what my knowledge tells me at the moment. But as I said, porosity wise, you are still okay if you don't make it, as long as it is properly organized and feature is, I mean, it is not a, it is a more or less a defect free material, perhaps it will be better. This is, as I said, once again, I might be wrong here, and this is what my knowledge tells me.
Thank you, sir.
Good evening, sir.
Good evening.
My question is, can I use MOF to remove heavy metals from water?
Yeah, you can. But technically, please keep it in mind that, as I said already, before you go into a particular application or particular property, please think that can I use something else other than the MOF? Just because I have to use a MOF for some purpose does not necessarily mean that I should do it. Can I use other materials for that? If I can use other materials, then we don't need to. But yes, heavy metals can be separated using it.
Is it selective for some metals or something like that?
It is generally, in my opinion, it's a surface adsorption only. It is not it is not going in the pore. It is not going. So your pore will remain, more or less unused. So why on earth I will use a MOF unless until I have a very large surface area or very large pore MOF. If I can make, yes, probably I can use it. But those kind of MOFs are also very challenging to make. So therefore, why shall I make a MOF and go for a heavy metal when I can do the same thing with porous carbon or zeolites as well, isn't it? Unless it gives a special feature. If it I mean, if the MOF shows a better job than the zeolite or the porous carbon, sure, of course, why not? Okay. But remember, they will be surface adsorption only. They will not go in the pore, the heavy metal. At least that's what I believe.
Thank you, sir.
Okay.
Do we have any more questions?
Yes, we are done.
Yeah.
Yes, good.
Okay, but
Well,
I would like to request Dr. Banerjee to be on stage for a few seconds as we welcome Professor Kari Rasen to the stage to present a small token of appreciation from the organizers, the GIAN, and as well as our Isaac Kolkata. Everyone, we have a few more announcements to go, so please be here. First, the snacks are here. So I know that many of you are quite hungry after a long day. And before you all leave for the snacks, you know what's tomorrow? You have got a test. Okay. So do you want some hints for it? You do know that you need to pass the test to get the course material, right? Sorry, not to get the course certificate. You want some hints or that's the end? Okay. So you all must have received some PDFs, presentations, and all those materials, right? Don't worry, the questions will be from them only. Okay. So study well. Tomorrow, 2 p.m. to 3 p.m. at LHC 213. The email will also contain the venue and time details. So that's all. Thank you all for joining.